So in this video we're going to be talking about the other major circuit analysis technique we use, which is called mesh analysis, which again, this really isn't anything new. This is just using KVL to analyze circuits. So what we do is we use loops. And in fact, some textbooks don't call it mesh analysis, they call it loop analysis. Mesh is in my opinion, the more standard name that is accepted in electrical engineering, but some people do use loops, or they'll say the mesh loop method, because we're really looking at loops here using KVL to analyze our circuits. Now, this is typically used to find currents. Now again, that doesn't mean it's the only way you would use mesh analysis is to find currents. Sometimes you would use it to find a voltage, but typically we use it to find currents. So let's look at a simple example here just to get our feet wet on mesh analysis here. So we're going to look at this problem right here. So here with this here, what we're asked to find here is this voltage here, V out. So the voltage drop across the 8 ohm resistor. Now, when we do this here, I'm going to erase that for now just so I don't get my circuit too clogged up, but basically finding the voltage across the 8 ohm resistor. And even though we don't necessarily use nodes, I always like to still kind of remind ourselves that, we let the ground here be 0 volts here is the bottom, what we're going to let it be. Now, when we do the loops here, there's more than one loop you can draw. You can draw lots of different loops. Typically, though, what I do is I draw the obvious loops. And what I mean is I say, okay, well, we've got a loop right here. And so I'll call that loop 1. And we have a loop here, which I'll consider loop 2. And then I got a loop here, which I'll consider loop 3. And I typically draw them all clockwise, unless it's obvious that I should draw it counterclockwise. And an obvious way to draw it counterclockwise would be, for instance, I'll just show this here and change it. If I had a current source going up like that, honestly, I'd want to draw loop 3 in the other direction, because then I'd know that the current for 3 is actually just equal to that current supply. But since it's not a current supply and it's just a voltage, I tend to draw all of mine counterclockwise. Now, when we do this, again, we're writing a KVL loop here. So what we want to do here is we want to, first off, anytime you hit the resistors with these arrows, they're always going to be considered in the positive direction. So what I mean by that is we'd have the voltage across the 2 ohm resistor plus the voltage across the 8 ohm resistor, and then we're coming into the negative side of that 40 ohm power supply, so it'd be minus 40 equals 0. And this would be for loop 1. And for loop 2, we would have the voltage across the 8 ohm resistor plus the voltage across the 6 ohm resistor plus another voltage across another 6 ohm resistor, and that would be equal to 0 because there's no power supplies in this, so this would be loop 2. And then loop 3, we'd have the voltage across the 6 ohm resistor plus the voltage across the 4 ohm resistor plus 20 volts is equal to 0. And it's plus 20 because I'm hitting the positive side of that power supply. So this would be loop 3. Now the problem we have right now is we have too many unknowns. Well, just like we did with nodal analysis, we're going to use Ohm's law to rewrite these voltages. So we're actually going to use Ohm's law to rewrite voltages as currents. So let's examine this first equation here. And I'm not going to rewrite the equation, but we have the voltage across the 2 ohm resistor. Well, we know that voltage, Ohm's law, is equal to current times resistance. So, well, what's the current going through here? Well, that's where these loops, I've labeled them 1, 2, and 3, but these loops actually represent currents. That's the current in loop 1. This is the current in loop 2. This is the current in loop 3. So if these are representing currents then, well, the current in I1 here, I'm hitting this 2 ohm resistor here, and I can see this branch, there's no other loops hitting this branch other than I1. So the current through the 2 ohm resistor is just simply I1. So my voltage would be I1 times 2. And now I know we would typically write it as 2I1, but I'm just doing it I times R. Now the 8 ohm resistor, we have to be a little bit more careful because what's the current going through this 8 ohm resistor? Well, I've got two currents touching this branch here. Now it's always going to be, whatever loop you're in is always going to be positive. So it's going to be plus an I1, but then I have to determine, is this negative or positive? So is it minus I2 or is it plus I2? Because I've got I1 and I2 touching the 8 ohm resistor, so both of those currents are going through that. It's actually a net of just a simple current, but we're looking at these as loops here. But then if I see here, well, I1 is going down, I2 is going up. So that means they're going against each other. And if they're going against each other, it's subtraction. So it would be I1 minus I2 times 8 ohms. Now, I'm going to take a pause here. Well, actually, let me finish writing the equation. Continuing on with this loop here, we'd get minus 40 equals 0. So now I have a new loop equation. Now, before I simplify this or modify this any, I want to emphasize here that if I had, for instance, drawn the loop counterclockwise, if I had drawn it counterclockwise like this, then I2 would also be going down, and I would have I1 plus I2 because they're both going down. But I drew it clockwise, and one is going down and the other is coming up. So that's why it's a negative or a subtraction there. So let's simplify this equation a little bit, and I'll just simplify it here. It's pretty easy to do. So we'd have 2 plus 8, so I'd have 10 I1. And then I have minus I2 times 8, so I have minus 8 I2. And then move the 40 over to the other side is equal to 40. All right, so we've got my first equation. It's got two unknowns in it. All right, so let's move on to the next loop. So the next loop would be I2, and I'll go ahead and do this one in blue. So we're going to go down and move it here. Now you can start anywhere in the loop. We have it as the 8 ohm. Now remember, whatever loop you're in is always the positive direction. So I'm in loop 2, so I2 is positive. So I'm looking at the 8 ohm resistor again right now, so it's positive I2. Now I2 is going up, I1 is going down, so they're in the opposite direction, so it'd be I2 minus I1, because whatever loop you're in is the positive direction. And then I still have to multiply it by the resistance, times 8. And then I have this 6 ohm up here, but if I look, this current going through this 6 ohm, only I2 is touching that resistor. So it'd be plus I2 times 6. And then we've got this other 6 ohm resistor, but that 6 ohm resistor has both I2 and I3 touching it. And again, I2 is always in the positive direction, and then this is going down, but then I3 would be going up. So this would be minus I3 because they're in the opposite direction, times 6. And this is all equal to 0. Then if you simplify that equation, you wind up with minus 8I1 plus 20I2, because you have 8 plus 6 plus 6, and then minus 6I3 equals 0. Now I did that simplification without, multiplying anything out and showing it, but at this point we should be able to do those simplifications without me showing you all the steps. And now finally we have to work on, I'll switch back to black, we have to work on this equation and rewriting it with currents here. So we start at the 6 ohm, and again I'm in loop 3 now, so I3 is automatically the positive one, and then I2 is in the opposite direction, so it'd be minus I2 times 6 plus, well, the 4 ohm only has I2 touching it, so it's 4I2, and then I'm hitting the positive side of the voltage source, so it's plus 20, and that's equal to 0, which again, if I simplify that, I would wind up with this should not be I2, this should be I3 because it's in the third loop there, negative 6I2 plus 10I3 is equal to negative 20. And so if we want to make sure that we have this nice and clean, my system of equations, I have 10I1 minus 8I2 plus 0I3 equals 40, minus 8I1 plus 20I2 minus 6I3 is equal to 0, and then 0I1 minus 6I2 plus 10I3 equals negative 20. Now, technically, it's still possible to solve this system of equations by hand. I would definitely go to my calculator to solve it. And if you use your calculator to solve this, you wind up with getting I1 is equal to 5.6 amps, I2 is equal to 2 amps, and I3 is equal to negative 0.8 amps. Now, let's go back up and see exactly what we were asked to find here. I found all these currents, but again, what am I asked to find in this case? I was supposed to find the voltage across the 8 ohm resistor, and it was labeled this way. That was what I was supposed to find, that output voltage. So that output voltage is the voltage across the 8 ohm resistor. Well, we've got two mesh loops here, two loop currents touching that resistor, but now we have to figure out, is it I1 minus I2 or I2 minus I1? And it's purely based off of the positive sign. I1 is hitting the positive sign, so I'd have plus I1. I2 is hitting the negative side, so minus I2. This is equal to the current through the 8 ohm resistor. So the current through the 8 ohm resistor is equal to 5.6 amps minus 2 amps, which would be 3.6 amps. And so then the voltage on the output is 3.6 amps times that 8 ohm resistor, which if we do that, use my calculator again here to make sure I don't make a silly algebraic mistake, we get 28.8 volts as the voltage across that resistor, V out. So this was showing loop analysis here. So we can see it's just, instead of doing nodes, we're literally doing loops. Now, once we get used to this, and I'm going to do it in the next example, not in this video, but the next example, we're going to typically not write these equations. So we'll typically not write. We'll typically go straight to these equations, but remembering that what we're doing is we're summing voltages up in a loop because we're using KVL, but what we're doing is we're using Ohm's law to write those voltages as a current times a resistance. But we are still absolutely summing voltages up. And so that's how that's mesh analysis. And honestly, this was a great problem. It was a system of 3 equations, 3 unknowns. I said we'll look at another one in the next video.